So let's see. Um, take any epsilon greater than zero. Um, we definitely have some k such that xk is between t and t plus epsilon. So let's draw a picture here. So a picture looks something like this. Say this is the interval from 0 to 1. Here is t, here is t plus epsilon, and on xk is somewhere here. So this k is a specific index that lies inside this interval. And this is any epsilon. Okay. Now, what we want to show is some magic here. So let's write distance x. Let's try L to be the distance of xk minus t. So this distance right here, it's L. All right. And now we can be specific because our xk is this n theta, right? So this is equal to some fractional part of k theta. Okay, so let's write it like this instead. So this is k theta minus t. Okay, so let's take a generic n theta and compare with this. So let's examine xn in general. Uh, and L. Well, what can we say about this? Well, this is equal to theta minus a fractional part to theta plus t, which um, inside fraction part, we can just remove the fraction part. So this is a theta, well, n minus k quantity theta plus t, like that. So I'm employing this property that if we have a number x plus y like that, that should be x plus y. That. Okay. Well, What can you say about this quantity? That's a good question. Um, hmm. Well, when you subtract an L, there are two things that happens. Right? So L is a number less than one. So let's analyze the two situations that could happen. So either we are, so this is, let's say 0, 1, and let's say for the sake of argument that this is our n theta, and where is n theta minus, well, let's say L is this much, right? So let's say you went back, well, let's just try to be to scale of what I drew. So let's say I went back here like that. So over here, that is going to be n theta minus L, and this is equal to n theta minus L like that. So in this case, so here this L right here is a number between 0 and 1, and this first case I'm describing is this is when n theta is bigger than L. Okay, so we got that. Mm, Bigger than or equal to L. This will underlie this case, right? Okay, so we got this, and well, all right. So that's one case. This is where n theta minus L is, and another case is that n theta is smaller than L. Okay, now this is going to be interesting because now we're going to get a wraparound situation. Right, so let's say we draw a unit interval from 0 to 1. Okay, so let's say n theta is right here, and we're going to subtract L, which now hops over like that. So now we land over here. So this point right here, this is going to be n theta minus, which we know this is n theta. Well, we know that n theta minus L is equal to equal to what? Equal uh to right, 1 minus quantity minus n theta, which is just 1 plus theta minus L. Okay, so at this second case. All right. And what do we want to say here? Well, What's the difference between these two things? Well, in the first case, it is, okay. So we have these two cases, right? So let's write them down. For the first case, we get um this part right here, and the second case here. Okay. So the first case we get n theta minus L. This is if n theta is greater or equal to L. Second case is 1 plus n theta minus L. This is if n theta is less than L. So let's now look at the difference. N theta minus n theta minus L. This is going to be interesting because in the first case, we get two cases. In the first case, we get L. This is if n theta is greater than equal to L. In the second case, as you see in the picture, n theta minus n theta minus L, because it's going to be smaller, it's going to be a negative number. This is a negative number. If n theta is less than L, right? Conclusion, however, is that n theta minus n theta minus L is uh less than or equal to L because L is positive and the negatives are less than this, and L is less than epsilon. Okay, so this is a interesting conclusion, intermediate conclusion. And let's see. Um, let's put everything back in here. So this says n theta minus n. So if you will see over here, L, right, it's right here, right? This is n minus k quantity theta plus t. This subtraction is always less than epsilon for all integers. Okay, so that's interesting. So this is going to help us finish the job because let us try to calculate this difference. This average, difference in average. Let's see. So the sum of n go from 1 to big N of n theta minus the sum n go from 1 to big N of n theta plus t. Okay, for t a number between 0 and 1. How can we bound this? Well, we have this k earlier, right? With this relation to this epsilon. So let's break this up. So let's break this up into some angle from 1 to k of theta plus some angle from k plus 1 to big 1 of n theta. And the second part, we're going to do something sneaky. We're going to change the index. So I'm going to change the inside index by n to n minus k. Remember, k is that fixed choice that we made in relation to epsilon, like this. And so if I drop the n by k inside the bounds, I need to raise it by k. So this is k plus 1 to n plus k, like that. What's interesting now I can combine this k plus 1 to n term, which I will do. And theta plus summation and go from this step, took me some time to work out for some bizarre reason. But anyway, so I have subtract 1 n minus k theta plus t. Okay, so that's one thing. Plus summation and go from big N plus 1 to big N plus 1 to uh, big N plus k of quantity n minus k quantity theta plus t, like that. Okay, so now let's bound this. Let's now bound this. The first term right here, this guy, it's all numbers between 0 and 1, right? And there's k of those. Also, we have a subtraction here. So this is a subtraction here. So let's think about this a little bit. Um, the first summation are numbers all between 0, 1, and well, this part is, and this part right here is also in 0, 1. And we can put them together, k terms and k terms. So k numbers between 0 and 1 minus k numbers between 0 and 1 gives you a number at most k, right? Yeah. So first and foremost, that is at most k between these two yellow ones. And this middle one right here, this guy, that one we showed is less than epsilon, right? From previous, from this one right here. So this is less than epsilon. So we now have this plus, so how many terms is that? Well, that's at most k n terms, right? K is a fixed number, but goes up to n, so will be egregious. This is less than n epsilon. Okay, so now we are cooking. This then means if I were to divide 1 over n to everything, Let's look at this difference of averages. Let's see what we get. Asian and go from 1 to big N of n theta plus t. By our inequality, this shows that this is less than or equal to k plus, well, rather, k over n plus epsilon. Now, if you take the lim sup of both sides, the right-hand side converges to epsilon. So this implies that the lim sup of 1 over n summation and go from 1 to big N of n theta minus 1 over n and go from 1 to big N of n theta plus t is less than or equal to epsilon. Huh. And we see what we're about to do is we're going to show the lim inf is the other way around. So if we can show that the lim inf is greater than negative epsilon and epsilon is arbitrary, then we show that the limit is actually 0. Right? So because here this epsilon is arbitrary. So you know that the lim sup of above quantity, this difference of averages, is less than or equal to 0. Okay. Similarly, what we're going to do is we're going to do something similar and pick XL um, pick for epsilon, for any epsilon greater than 0, and t and 1. Well, we'll use xk again. Pick xk such that what we now want this picture. We have 0, we have 1, we have this is t minus epsilon. Let's now take this here. Okay, so can we reconstruct this argument? Let's see. Mm, see here. Let's for the distance between. So now we want to what? We want to bound things above. That's right. Again, L to be the distance of t minus theta. And what happens for any positive integer n? Let's examine the same thing n theta plus L this time. Yeah, so what I want? Well, I don't know. Let's just try it. Let's just try it. I have no idea. So okay, couple cases, right? So let's say this is n theta, and let's say L is this big. Now we're at n theta plus L. I still think we want to subtract L, right? Hmm. Now here, this is if like that. Or in the other case, here's n theta, and then if we add L, it comes up over here. So what can we say? Hmm, couple things. In the first case, the distance is exactly equal to minus L, and minus L is this L is less than or equal to epsilon. Actually, it's less than epsilon, and L is positive, right? And so what? So L is less than epsilon. L is less than epsilon. L is less than epsilon, so minus L is greater than minus epsilon. So that we know this is, in that case, is equal to L, no, equal to minus L, so this is greater than minus epsilon, right? And in the first case, this is true. In the second case, n theta is bigger than, right, so it's either positive. So there are two cases here. In the first case, this is equal to minus L, which is greater than minus epsilon, if n theta plus L is less than or equal to 1, or it's just positive. And if it's positive, then of course, if it's positive, of course, it's greater than minus epsilon. So in either case, it's all greater than minus epsilon. Great. So now we can leverage this fact. How are we going to leverage this fact? Well, n theta plus L is equal to n theta plus what is L, right? L is t minus k theta. T minus, so this is again n minus k quantity theta plus t like that. And is that right? Yeah, I guess so. So we now look at the difference in averages, difference in the sum first, and go from 1 to big N of n theta minus summation, and go from 1 to big N of n theta plus t, which is what we want to analyze. Again, this ends from 1 to big 1 to k, specified by the epsilon of n theta plus summation, and go from 1, sorry, k plus 1 to big N of n theta minus, and now we change some index here. I want to change the same index as n minus k here, so here is going to add k to this. Like that. We now combine. K to n of n theta minus n minus k theta plus t. So this just very nicely bounds this part. And then minus, and go from n plus 1 to n plus k of this remaining junk. And now let's do some boundy bounds. Again, each of these numbers is between 0 and 1. There are k of those. Each of these numbers is between 0 and 1, and there's k of those. So first, mm, so that's definitely bigger than minus k, right? Because, this could be 0, this could be minus 1, so the worst case scenario is minus 1, minus 1, dot, 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 dot. Yeah. And then this middle term right here by this star star situation, we know this is bigger than epsilon minus epsilon. And so this is bigger than, and there are n of those, so minus n epsilon. Now we are in business because therefore, by taking the average, this, this, theta plus t, this is bigger than or equal to minus k over big N minus epsilon. So take the limbs, lim inf, the difference of the averages is greater than or equal to minus epsilon. And as epsilon is arbitrary, we have that the lim inf of the difference in averages to be greater than 0. And now we have our situation. The lim sup is less than or equal to 0. The lim inf is bigger than or equal to 0. So the lim sup and lim inf are both equal to 0, which means the limit equals to 0. So conclusion, 0 less than or equal to the lim inf of dot dot dot, which of course is less than or equal to the lim sup dot dot dot, which is less than or equal to 0, which means the lim sup of dot 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 is equal to the lim inf dot dot dot, which is equal to 0, which is the limit. So, yep. Hey, okay. So this shows it satisfied this criteria, right?